Your outside outlet keeps going dead. Every time it rains, it trips, and you walk out, push the little button, and a day later it's tripped again. Today, let's find out exactly why. With the math. That outlet is protected by a GFCI, a ground fault circuit interrupter, and once you see the one equation inside it, every single nuisance trip is going to make sense. Here's the first surprise. A GFCI does not measure how much current is leaking to ground. It watches for an imbalance. Both wires, the hot and the neutral, pass through a small sensing ring inside the device. Normally, every bit of current that flows out on the hot comes right back on the neutral, equal and opposite. So we can write it as Kirchhoff's current law. The hot current minus the neutral current equals the leakage current. When everything's healthy, those two are equal. Hot minus neutral is 0. Nothing is leaking, and the GFCI sits perfectly still. But now suppose some current finds another way back to ground, through water, through wet insulation, or through a person. That current leaves on the hot, but it does not return on the neutral. It went to ground instead. Now hot minus neutral is not 0. The sensing ring sees that difference, and the difference is the leakage current. One more detail that trips people up. The ground wire does not pass through the ring. That's why a GFCI can protect even an old 2-wire outlet with no ground at all. The moment that imbalance gets big enough, the GFCI snaps the circuit open. That's your trip. So the real question is, how big is big enough? The standard says 6 milliamps, 6 thousandths of 1 amp, and it must trip. Below 4 milliamps, it must not trip. So the whole decision lives in a tiny band, 4 to 6 milliamps. Hold on to that 6. Now, why does rain specifically set it off? Let's do the math. Water hands the current a brand new path to ground, and every path has resistance. Ohm's law tells us exactly how much leaks away. Current equals voltage over resistance. Our voltage is 120 volts. Our trip current is 6 milliamps. So the resistance that just trips it is 120 divided by 0.006. That comes out to 20,000 ohms. 20 kilo ohms. Sit with what that means. Any wet path to ground below about 20,000 ohms will trip your GFCI, a damp outlet box, a film of water across the contacts, wet aging insulation on an extension cord. Those all land right in that zone. But rain isn't the only cause, because leakage adds up. Every appliance is allowed to leak a tiny trickle to ground, up to about 3/4 of a milliamp each. 1 or 2 you'll never notice, but 8 of them, 8 times 0.75 is 6 milliamps. The circuit trips, with nothing actually broken. That's why it lets go the instant you plug in one more thing. It's Kirchhoff again. The little leakages simply add up to the limit. And here's the strangest one. It trips with nothing plugged in at all. That's a neutral wire touching ground somewhere past the GFCI. That gives return current a second path that skips the sensing ring. Imbalance at 0 load. The device is built to catch exactly that fault. So, is a GFCI that keeps tripping broken? It's the opposite. Here's the math that matters most. If your wet body ever bridged that circuit, your resistance is only about 1,000 ohms. So the current would be 120 over 1,000. That's 120 milliamps. Right in the range that stops a human heart. Your GFCI trips at 6, 20 times lower, and long before that current could ever build up through you. That 6 milliamp number isn't arbitrary. It comes from Charles Dalzell, who patented this device back in 1965. 6 milliamps is about where almost anyone can still let go of a live wire. So the next time it trips in the rain, that's not a failure. That's the device doing its one job, airing toward your heart. Grab a pencil and let's work a few. See you at the board.